Today we will continue our discussion of Thevenin and Norton equivalent circuits, and we will also start the subject of maximum power transfer. But before we get started, let's review some of what we've already discussed. We have two problems here from the FE preview exam, and I want to find the Thevenin equivalent resistance and the Thevenin equivalent voltage for the first circuit and the Norton equivalent source and resistance for the second circuit. So let's look here. We have a 60 volt source in parallel with a 16 ohm resistor in series with a 4 ohm resistor, and that entire quantity in parallel with 12 ohms. Remember, the quick way to find the equivalent resistance is to turn off the independent sources. So if I turn off the 60 volt source, it becomes a short, and that's in parallel with the 16 ohm resistor, which is in series with the 4 ohm resistor, and that's in parallel with the 12 ohm resistor. So the question becomes, what happens to the 16 ohm resistor when I turn off the voltage source? We talked about this in the last lecture. That resistor is shorted out, which means the voltage is zero, the current is zero. It has no effect on the analysis. So once I remove that 16 ohm resistor, what I have left is 12 in parallel with 4, which is 3 ohms. Since there's only one of the choices that has a 3 ohm resistor for our Thevenin, I know that the answer is A. However, for good practice, let's go ahead and find V Thevenin as well. V Thevenin is the open circuit voltage between terminals A and B. I can actually use the voltage divider to find that value by noting that this node has a voltage of 60 volts with respect to ground. So the voltage divider would be 12 divided by 4 plus 12 times 60. 12 divided by 4 plus 12 times 60 is indeed 45 volts. So V Thevenin is 45 volts and R Thevenin is 3 ohms. Okay, let's try another one. Here I have a 20 volt source, a 10 volt source, and a 10 ohm resistor in series, and all of those are in parallel with the 10 ohm resistor. So the first thing I can do is turn off the sources to find our Thevenin. Both voltage sources become shorts, and I have a 10 ohm resistor at the bottom of the circuit and a 10 ohm resistor between terminals A and B. Those two resistors at this point are in parallel. 10 in parallel with 10 is 5 ohms. So that means my answer is either A or C, but we've got to do more work to figure out which one is correct. I can redraw the circuit by combining the voltage sources. I have 20 volt voltage rise and a 10 volt drop, which gives me a net 10 volts in series with the 10 ohm resistor. Notice it doesn't matter whether I put the 10 ohm resistor on top or bottom, so I'll put it on the top. There's the 10 ohms, and then I have the 10 ohm between terminals A and B. If I do a source transformation on this circuit, 10 divided by 10 gives me a 1 amp current source, and that's going to be in parallel with the two 10 ohm resistors, so those two combined become 5 ohms. So the Norton equivalent circuit is a 1 amp current source in parallel with a 5 ohm resistor, which means the correct answer is C. Okay, let's find the Thevenin and Norton equivalent of a circuit that includes dependent sources. Let's try this one. If I want to find the open circuit voltage, which is the voltage between terminals A and B, I can find the voltage across the 15 ohm resistor. So I'm going to draw a clockwise current, and we'll write the KVL equation for that loop. We'll have 15I plus 5I plus 10I plus 4Vx equals 0. And because we have a dependent source, that always creates a constraint equation. So my constraint equation is going to be negative 5I. It's important not to forget the minus sign. Why is there a minus sign? The current goes in at the negative and out of the positive, so that would not obey the passive sign convention with the way it's drawn, so I have to put a minus sign here. So now we want to solve for I, because remember, V Thevenin is going to equal 15 times I. So when I substitute Vx equals negative 5I into the first equation, I get 15I plus 5I plus 10I minus 20I equals 0. That's one equation and one unknown. So when I solve for I is equal to 0 amps. Which means that Thevenin, which is the voltage across the 15 ohm resistor, is equal to 0 volts. Why? This leads to one of our special cases, and I'll write it up here. Whenever you have a circuit with no independent sources, Thevenin is equal to 0 volts, and I Norton is equal to 0 amps. That is very important. Remember that. Whenever you have a circuit with no independent sources, Thevenin is equal to 0 volts, I Norton is equal to 0 amps. So the question becomes, how do we find Thevenin? I can't divide because Thevenin would be equal to 0 over 0, which is undefined. However, the last technique we'll discuss, and we talked about this during our last lecture, is the test source method. For the test source method, you put either a voltage source or a current source across terminals A and B, and Thevenin is going to equal V test over I test. Remember, if when you do this, V test or I test is a negative number, you take the absolute value. You don't ever give a negative resistance as your final answer. So I'm going to redraw our circuit, and I'm going to add a test voltage source. There's the 10 ohms, 5 ohms, Vx, 4 Vx, 15 ohms, and over here at terminals A and B, I'm going to put a voltage source V test equal to 1 volt, and the current through that voltage source is going to be I test. To solve this problem, I'm going to stick with the mesh analysis. So I'll label my clockwise current again, I. And the equation is going to be 15 times I plus I test plus 5I plus 10I minus 4Vx, and that equals 0. The constraint is once again Vx equals negative 5I. Now for this right mesh, I have a counterclockwise current I test, so I'm going to have 15 times I plus I test is equal to 1. So now I can solve for my unknown values, and I'll have I is equal to 0.2 amps. I test is equal to negative 2 over 15 amps. So our Thevenin would be V test over I test, which is 15 over 2 or 7.5 ohms. Remember, we never put the negative sign for the current because we don't want a negative resistance. So for this example, the Thevenin and Norton equivalent circuit looks the same because it's just a resistor. So what you would draw is a 7.5 ohm resistor between terminals A and B. So recall, the primary purpose for doing Thevenin and Norton equivalent circuits is because I'm more interested in the terminal characteristics of the circuit than what's going on inside the circuit. In other words, I want to know the voltage, the current, or the power delivered to a load that's attached to that circuit. This is called maximum power transfer, which involves determining the value of a load resistor that permits maximum power delivery. Remember, we represent this load resistor as a potentiometer or variable resistor. That's why it has the arrow through it, because we can actually vary the resistor value to determine when that maximum power occurs. You will have a lab where you do this. If you look at our graph, we vary the load resistor over several values and measure the power delivered to the load. When the power is maximized, the load resistor is equal to R Thevenin. One of the questions you're always asked on exam is, what's the value of the load resistor that guarantees maximum power delivery? The answer to that question is always when RL equals R Thevenin. Once you replace RL with a value of R Thevenin, you calculate the power delivered. You can go through and do KVL or KCL or the voltage divider in order to find the voltage across the load and the current through the load and multiply those two together. However, there is a formula that you could use for maximum power transfer, but it only works when the load is equal to R Thevenin, and it's derived for you here. The KVL equation would be negative V Thevenin plus IR Thevenin plus IRL equals 0. When you solve for the current, you have V Thevenin over R Thevenin plus RL. So the power would be equal to I squared times RL. And since R Thevenin equals RL, that simplifies to P max equals V Thevenin squared over 4RL. Do not forget, this only works when R Thevenin equals RL. Okay, let's revisit a problem we solved before in order to find the maximum power transferred to a load. This is the circuit we solved a couple of lectures ago using source transformation. So recall that the Thevenin equivalent circuit was a 30-volt source in series with a 4-ohm resistor. That's V Thevenin and R Thevenin. So if the question is, what value resistor should you place across terminals A and B for maximum power transfer, the answer is that RL should equal R Thevenin, which is 4 ohms for maximum power transfer. So I put a load resistor here with a value of 4 ohms, and P max is equal to V Thevenin squared over 4RL, which is 30 squared over 4 times 4. So the maximum power delivered to the load would be 56.25 watts. Okay, now let's try an example that has a combination of independent and dependent sources. For the following circuit, find the value of a load resistor for maximum power transferred. Now recall, you're going to have to find the Thevenin equivalent circuit in order to do this problem. So let's find the open circuit voltage between terminals A and B first, and that'll give us V Thevenin. Our dependent voltage source is in parallel with a 2-ohm resistor, and that voltage source is not tied to ground. So this creates a supernode. Recall that when we have a supernode, we have to do KVL and KCL at the supernode. So let's do KVL first. The KVL equation, if I name this node Vx because it's already labeled, and I name this node V Thevenin because it's already labeled, why is this node V Thevenin? If this is an open circuit, there's no current flowing through the 2-ohm resistor, which means the voltage drop is 0. So the voltage at node A is the same as the voltage at the node on the left side of the 2-ohm resistor. So my KVL equation is going to be, therefore the KVL equation is going to be V Thevenin minus Vx equals 2Vx. The KCL equation is going to be, Vx over 4 plus V Thevenin over 6 equals 5. Notice we have 2 equations and 2 unknowns. So for this particular problem, we don't need a constraint equation. And we'll solve Vx is equal to 20 over 3 volts. And V Thevenin is equal to 20 volts. So now we need the Thevenin equivalent resistance. We're actually going to use the test source method to do this. Remember, when you have a dependent source, you can do the test source method, but you need to turn off the independent sources. So the first thing I'm going to do is to turn off that 5 amp current source. It becomes an open circuit, and then you copy down the rest of the circuit. So I have 4 ohms, Vx, 2 ohms, 6 ohms, 2 ohms, and then across the top I have that dependent voltage source again. You can never ever turn off a dependent source. So it's negative plus 2Vx. And now I can put either a current source or a voltage source. How do I decide? Well, if I know I'm going to do the mesh current method, then a current source may be better because that's one less mesh where I have to do KVL. Or if I know I'm going to do the node voltage method, a voltage source may be better because that's one less node where I have to do KCL. Sometimes it just doesn't really matter. So for this one, I'm going to put I test equal to 1 amp. And what we're looking for is V test. I'm going to stick with KCL, or the node voltage method. And once again, I have a super node here. So if I name these nodes, this one is now Vx, and this one has a new name. Let's call it V1. So KVL at the supernode is now V1 minus Vx equals 2Vx. And KCL at the supernode is Vx over 4 plus V1 over 6 equals 1. Why does it equal 1? Because the 1 amp goes up and to the left through the 2 ohm resistor. So there's 1 amp coming in there. So now we have 2 equations and 2 unknowns once again. So when I solve, I get V1 is equal to 4 volts. Vx is equal to 4 over 3 volts. So V test will be equal to V1 plus the voltage across the 2 ohm resistor in series with the current source. So V test is going to be equal to 4 plus 2, which equals 6 ohms. So our Thevenin is equal to V test over I test. So our Thevenin is equal to 6 ohms. So now that we have V Thevenin and R Thevenin, we know that for maximum power transfer, RL equals R load, which equals 6 ohms. And the maximum power that's transferred to that load is V Thevenin squared over 4 RL, or 20 squared over 4 times 6. So the maximum power is 16.67 watts.